In 2004, in the Chinese city of Wuzhou, engineers picked up an 8-story apartment building, all 15,000 tons of it, and walked it 36 meters across the ground. Not brick by brick. Not demolished and rebuilt. The whole thing moved in one piece, with the windows in place and the tiles still on the walls. A building is designed to do exactly one thing forever, which is stay perfectly still. So how do you lift something that heavy off its foundations, roll it to a new spot, and set it back down without the entire structure tearing itself apart? The answer is one of the strangest and most precise tricks in all of engineering. By the end of this, you will understand how engineers move a building that was never meant to leave the ground, and why the hardest part is not the weight at all. You will see that the real enemy is something almost invisible, a difference of just a few millimeters, and that beating it comes down to a single idea. Not brute force, but perfect synchronization. Let's start with why a building fights back the moment you try to move it. Here is the first surprise. The weight of a building is not really the problem. We have machines that can push almost unimaginable loads. The problem is that a building is rigid and brittle. Concrete is fantastic at being squeezed, but it hates being bent or twisted. Engineers have a word for this. Concrete is strong in compression but weak in tension, which is why it is normally laced with steel bars to handle any pulling forces. A building standing still has all of that carefully balanced, but lifting it introduces brand new forces the designers never planned for. If you lift a long building and one corner rises even slightly faster than the others, the structure begins to flex, and parts of it that were only ever meant to be squeezed suddenly find themselves being stretched. And a structure that was never designed to flex responds the only way it can. It cracks. So the entire challenge of moving a building is not about strength. It is about keeping every single part of it moving in perfect lockstep, so that from the building's point of view, nothing is happening at all. It never feels twisted, never feels bent, and so it never cracks. Think of carrying a large sheet of glass flat on your open hands. Lift both hands together and it travels safely. Let one hand rise a little faster than the other and it shatters. A building is that sheet of glass, scaled up to thousands of tons. Everything that follows is just clever ways to guarantee that stillness while the ground beneath it changes. Before anything can move, the building has to be separated from its own foundations, and this is more delicate than it sounds. A building's weight normally flows straight down through its columns and walls into the foundation and out into the soil. To move it, engineers must intercept that flow of weight and reroute it into a new temporary support system. They dig in around and beneath the structure and build a rigid steel and concrete frame underneath it, threading massive beams through the columns just above the foundation. This new frame becomes an artificial floor that gathers up the entire weight of the building into a single connected raft. Only once that transfer frame is carrying the load do they cut the original columns, slicing the building free from the ground it has stood on, sometimes for a century. At that moment, the building is no longer attached to the earth. It is sitting on a tray. This step alone can take weeks of painstaking work, because every column has to be captured by the new frame before it is cut, and the cuts have to happen in a careful sequence so the building's weight is never left hanging on too few supports. Get that sequence wrong, even briefly, and part of the structure could sag before the frame is ready to catch it. Engineers effectively perform open-heart surgery on the building's skeleton, replacing its connection to the ground without ever letting it feel unsupported for a single moment. Now comes the lift, and this is where synchronization becomes everything. Engineers place a network of hydraulic jacks under that steel frame, sometimes dozens of them, sometimes well over 100. On the Wuzhou building, more than 100 jacks work together. A single hydraulic jack is simple. Pump oil into a cylinder and it pushes with enormous force. But if each jack pushed on its own at its own speed, the building would rack and shatter. So the jacks are all wired into one central computer-controlled system that acts like a single brain. Sensors watch the height at every point, hundreds of times a second, and the computer trims the oil pressure to each jack so that every part of the building rises at exactly the same rate. As it lifts, workers slide in stacks of heavy timber, called cribbing, laid in crisscrossing layers like a giant wooden log cabin, building up towers beneath the structure. This cribbing is the quiet hero of the whole operation. Wood stacked this way can carry astonishing loads, and it fails gracefully rather than suddenly, groaning and compressing before it ever gives way. So if a hydraulic line ever burst, the building would settle only a fraction of an inch onto solid timber rather than dropping. The jacks and the cribbing leapfrog each other. Jacks push the building up a few inches, workers pack in another layer of cribbing, the jacks reset higher, and the cycle repeats. The building rises in tiny, patient increments, always perfectly level, until there is room underneath for the machinery that will carry it away. On a big move, just this lifting phase can take days of careful, monitored work before the building has traveled a single horizontal inch. With the building floating on its steel tray, engineers slide the transport system underneath. The classic method is beautifully mechanical. They lay down parallel steel rails and place hundreds of steel rollers between the rails and the building's frame, turning the whole structure into the world's heaviest object on wheels. Then modest hydraulic rams push the entire building forward, and it glides along the rails at a walking pace so slow you can barely see it, often just a few meters an hour. The Wuzhou apartment block crept its 36 meters this way, on rollers nudged along by jacks. It sounds crude, but rolling on rails has a hidden advantage. The load is spread across so many contact points that no single roller is ever overwhelmed. And if the building needs to change direction, engineers simply lay a fresh set of rails at the new angle and shift it across. Some historic moves use this exact method to walk buildings around 90-degree corners, a few centimeters at a time. On the largest and most complex moves today, engineers use something even more advanced, self-propelled modular transporters. These are computer-coordinated platforms carrying huge grids of powered wheels, and each wheel can steer and lift independently. Hundreds of axles share the load and turn together, so a building can be driven around corners and over uneven ground while staying perfectly level. In one recent record, a 7,500-ton hotel in Sanya, China was driven 500 meters on more than 250 of these coordinated axle lines, steered around bends that a fixed rail system could never have managed. The same technology routinely lifts entire bridge spans and pieces of oil platforms, objects weighing tens of thousands of tons, and sets them down within a centimeter of their target. So why go to all this trouble instead of just pushing hard? Because of that invisible enemy from the beginning, differential movement. Imagine the building is being carried across a stretch of ground, and the soil under one side is very slightly softer than the other. That side sinks a few millimeters more. To you, a few millimeters is nothing. To a rigid concrete frame 40 meters long, that tiny tilt is a violent twist, enough to open cracks through walls and columns. This is why the technology is obsessed with sensors and computers rather than raw power. The self-propelled transporters constantly adjust the height of every wheel to erase those millimeter differences in real time, keeping the building flat no matter what the ground does. Engineers even split the wheels into groups that share pressure like the legs of a table resting on soft ground, so the load flows smoothly between them instead of concentrating on one point. It is the same principle as a hydraulic car lift, scaled up to the size of a city block and controlled to the millimeter. The genius of moving a building is not that engineers found a way to push something heavy. It is that they found a way to make a huge, brittle object believe, at every instant, that it is standing perfectly still. Every jack, every roller, every sensor exists to protect one fragile promise: that the building will never know it left home. It is fair to ask why anyone would attempt something so risky rather than just knocking the building down and starting over. Usually the answer is history. Many of these moves are done to save landmark buildings that sit in the path of a new road, a rail line, or a redevelopment. Rather than lose an irreplaceable old theater or town hall, a city spends the money to slide it a few hundred feet to safety. One of the most famous early examples was a telephone exchange building in Indiana that, in the 1930s, was rotated and shifted while it kept fully operating. 800 employees stayed at work inside. The switchboard never dropped a single call. And the gas, water, electricity, and sewer lines all flexed on special jointed connections that followed the building as it crept along. A full month of movement without one interrupted service. Sometimes the reason is engineering itself. It can be cheaper and far greener to relocate a sound structure than to demolish it and pour thousands of tons of new concrete, since concrete production is one of the largest sources of carbon emissions on the planet. And occasionally it is about lifting a building straight up to slide new foundations underneath, or to raise it above a rising flood line. In the United States, one of the 2,600-ton theater in Minnesota walked 3 city blocks to save it. Whatever the reason, the decision always comes down to one calculation. Is this building worth the extraordinary effort and expense of moving it in one piece rather than starting again? There are limits, of course. The taller and more slender a building, the harder it is to keep stable while it moves, because a tall tower behaves like a lever, amplifying any small tilt at the base into a large sway at the top. That is why the record-breaking moves tend to be relatively squat, heavy blocks rather than thin skyscrapers. The true heavyweight champion of building moves is a stone mansion in Baku, Azerbaijan, the house of Issa Bey Hajinsky, which weighed around 18,000 tons and was shifted to make way for a road, the heaviest building ever relocated in one piece. In China, engineers have even moved entire clusters of buildings at once, including a museum complex whose main hall alone weighed roughly 10,000 tons and stood over 40 meters tall. Each of these was, in effect, a small mountain of concrete and stone persuaded to take a short, perfectly level walk. Cost is the other wall. A major building move can run into the millions, and every additional obstacle, a curve in the route, a slope, soft ground, a utility line multiplies the difficulty. Engineers survey every inch of the path in advance, mapping the soil, reinforcing the ground where needed, and rehearsing the move meter by meter on a computer before a single jack is switched on. The route itself often has to be rebuilt. Soft soil gets compacted or paved with temporary steel road. Slopes are leveled, and anything buried underneath, pipes, cables, old foundations, has to be found and dealt with, because a hidden void beneath the path could let one side drop at the worst possible moment. Nothing about it is improvised. By the time the building actually rolls, the 100 times over in simulation, and the real move becomes almost an anticlimax, a slow, silent glide that the 100 times on their screens. So the next time you see a building and assume it is a permanent fixture, bolted to that one spot for good, remember Wuzhou. 15,000 tons of concrete and glass, lifted off the earth on a bed of jacks, rolled across the ground on steel wheels, and set back down as if it had always been there. The secret was never raw power. It was the patience to move every part of something enormous in perfect unison, so that a rigid, brittle giant could travel across the ground and never once feel itself move at all.